Hello, and in this statistics video I'm going to quickly show you how to calculate the one-way between groups ANOVA by hand. As I've talked about in previous videos, this is a technique for comparing two or more groups on one continuous dependent variable in terms of their means on that variable. The between groups part of it is saying that the people who contributed to our different conditions were different people. In other words, it wasn't a repeated measure design where the same person does multiple tasks. We had different people assigned to the different tasks. So we're going to look at how to calculate this by hand. In order to be able to calculate it, we need to calculate three things. We need to calculate the total variability in our data that we're going to try to explain. We're then going to partition that into the amount of variability that's created by our experimental effect and the amount of variability that's created by chance. And if the amount of variability created by our experimental effect is greater than the amount of variability created by chance, then we'll get a significant result. So let's stop talking and go and look at the data. This is the data here, and we've just got three groups here. Obviously you'd have many more than this, but this is just for demonstration purposes, and we've calculated the means of all our groups, and we want to see if there's a difference between those means. ANOVA requires that the error variances are the same between groups, and if we look at our standard deviations, which I've done a previous video on how to calculate, we can see that they're about the same. We're not testing out statistically, we're going to talk about that in a future video, but they're about the same. So the first thing we need to do is calculate the means of all of our different groups. So that's just the total of scores in the group divided by the number of scores. So in this case it's the total of waiting list divided by 5, the total of computerized CBT divided by 5, the total of in-person CBT divided by 5. We next need to calculate the grand mean, which can be thought of as the mean of means. So the average of all the means. There's 3 means, so we divide by 3 and get 5.8. So how do we actually do this? Well, the first thing we need to do is work out how much of the variability in our data, how much variability there is to explain. So in order to do that, we see move this over slightly, and just for our first score, I'm going to do it as an example. We need to take the deviation or the difference between our score and the overall mean. So 8 minus 5.8, the overall mean gives us a score of 2.20, and we're going to do that for all our scores. You see those here. We're then going to take that score of 2.20 or whatever score you've got, and we're gonna square it. Why are we going to do that? Well, we've seen in previous videos that some of these scores can be positive and some of them can be minuses, and if they were left as minuses, they would cancel each other out. So to get rid of that problem, we square them. Squared numbers cannot be negative. So once we've got that, here are all our squared deviations, and to get a measure of the total variability that's in our data, all we're going to do is add up those squared deviations. So there are 86.4 units of variability to squared units to explain in our data. Now, this is very similar to what we calculated for variance if you watched that video. So we said that this 86.4 units, some of it will be explained by error, just differences between peoples, and some of it will be explained by our model, which is the two groups we assigned. So how do we calculate the amount explained by each of those things? Well, we're going to start with error. So we're just going to use our first group as an example, and if our model is good, if it's just the groups that make the difference, then each score within one group should be the same, because there should be no other reason for there to be differences between groups. So in order to calculate the error, we're going to calculate the difference between an individual score and the mean, but instead of using the mean of all scores this time, we're going to calculate the difference between an individual score and that group. So for the first one, we get a score 8 minus the mean, which is 6.2 for this group, equals 1.8. And then, like we saw previously, some of them can be positive and some of them can be negative, so we're going to square the deviations, and we're then gonna add up those squared deviations in each group. So we know for the waiting list group there's 20.8 units of error variability differences between the scores that aren't different just because of the different groups. We reapply the process to all of our groups and we get a total of 66.6 units of variability. I've just done that for every group and added them together. So we know what's due to error and we know what the total variability is. So to get the amount of variability that's due to our experimental effect, what we can do is take advantage of the fact that we know that the total must be made up of our effect and some error, so we can rearrange that process to say if we know that the total is the effect plus error, the effect must be the total minus whatever the error is. So we apply that equation here and we get a sum of squares for our effect of 20.8. Just to show you another way you can get that is because our the whole point of an ANOVA is that our best guess of how we can explain variability and in our data is the different groups we've assigned people to. So a way you can get and measure the variability associated with your effect is the mean of the individual group minus the overall mean squared, and then times the number of people who contribute to that group. So each of our scores had 5 people in it, so our best estimate for each score within that group is the group mean, and you see again we get 20.8. So we have all these scores, but they're totals. What we want is averages, and to get the averages, obviously you need to take the total and divide by something, but it's not just dividing by the number of scores like you do for most means. It's this concept of degrees of freedom, or how many things that have contributed to your effect are free to vary. So as a general rule, this is the number of scores that were involved in the calculation minus the scores that have to be the same. So if you apply this to a situation of an overall mean, most means have degrees of freedom of the number of scores minus 1, because if you think about it, in order for an average to be what it is, or all the other scores could be different, but in order for the average to be true, the last score can only be one thing, so it's not free to vary. So the general formula is not number of scores minus number of scores that have to be fixed, but in terms of our effect or our experimental effect, we've got 3 groups, so the 3 means that are free to vary minus 1 equals 2, and where does that error variance come from? Well, it becomes from differences between individuals, so we're going to do the total number of scores minus the number of groups equals 12. So to get our averages, we then take the appropriate sum of squares and divide it by the degrees of freedom. So for our effect, we've got a mean sum of squares of 10.4, and for our error we've got a mean square of 5.46, and so certainly looks like we've got more just due to our effect than due to error. But how do we conceptualize these two? Well, we put them in something called an F ratio, which, if you go back to the previous slide, you'll notice that's our effect divided by our error. So because it's a ratio, if the effect and the error were the same, would be exactly 1. So because our ratio is positive and above 1.9, it means we've got marginally more error explained by our experimental effect than our error. But is this significant? Well, we look at the F value in a critical value table with the appropriate degrees of freedom. So as we just calculated, it's 1 and 3 in this case, and the probability value we get associated with that is 1.92. So that's much bigger than 0.05. So we get a non-significant effect. Okay, so that was a simple example of how to calculate a one-way ANOVA and the logic behind it. Thanks for watching, and I'll see you in the next video. Bye bye.